This unit of the course is about the Laplace transform. The formal definition will come later, but let me start with the idea. A transform in mathematics is an operation on functions that changes functions of one type to functions of another type. It's reinterpreting the whole situation, shifting everything into a new environment. Transforms are often very strange, and you'll see this strangeness in the Laplace transform throughout the videos in this unit. So why do such a thing? Why transform functions? Well, the hope is that by transforming, by changing the environment, by changing functions into new types, it can make certain problems easier. It's a radical method, making huge alterations to everything to see if a translation of the problem gets any easier, but it does turn out to work out pretty well in a number of circumstances. In our circumstances, the hope is that the Laplace transform will make differential equations easier to solve. And indeed it does. As I will show, a Laplace transform will change a dE into a normal equation, a non-differential equation. And that's a pretty remarkable thing. So let's get to the definition. As I said, the Laplace transform is a pretty weird thing, so this is going to be a strange definition. It will take some getting used to. To define the Laplace transform, I need one other definition first. This is a refinement of the idea of asymptotic order, focusing on functions that grow slower than particular exponential functions. Say that f is a function defined on the positive numbers. We say that f has exponential order c if the function is eventually smaller than some exponential function with exponential growth coefficient c. Formally, the absolute value of s is less than m times e to the ct. C is the growth coefficient, and m is a constant that forms part of the bounding function. This only needs to be true in the long run, so that is past some particular capital T. In the long term, the function is smaller than a constant times e to the ct. For those of you who know big O notation from asymptotic analysis, likely from computing science, this is the same as saying that f is in the class big O of e to the ct. Now I can make a definition of the Laplace transform. Let f be a piecewise continuous function defined for the positive numbers, and assume that f has exponential order c, as I just defined. Then the Laplace transform of f is a new function in a new variable s, which is given by this integral. The notation of L of f using these curly brackets is conventional. It is a function of s, so bracket s and bracket indicates that. The function is given by an integral from 0 to infinity of f multiplied by an exponential decay function, where s, the new variable, is the decay coefficient. The domain of this new function is c infinity, where the assumption was that f has exponential order c. And this is required for the integral to converge. This is an improper integral, so we need to worry about convergence. The control on the growth of the function, exponential order c, means that it is small enough, at least for certain values of s, for the integral to be finite. And that's why I needed exponential order. Again, this is strange. Each value of the new function is calculated by some improper integral. S is the variable, and changing the s inside the integral changes the rate of the decay of e to the negative st piece, which will then change the value of the whole integral. And the result is a new function of the variable s. Having a whole integral to calculate every value of the new function might seem very daunting, but I will show you that this works out much better than you might first expect. Before I get into examples, let me talk a little bit about notation. This is the general notation, script L with curly brackets. But there are some other conventions as well which are a bit easier to read. Typically, if lowercase f of t and lowercase g of t are functions, their Laplace transforms are indicated by uppercase versions, capital F of s and capital G of s. The variable before the transition is almost always t, and afterwards almost always s. Using these variable conventions, I will often talk about the t domain and the s domain, functions before and after Laplace transforms. So let's get into some examples of Laplace transforms. Let me caution you again, the Laplace transform is an extremely strange thing. There isn't a lot of intuition about what a function will actually transform into, but let's see what happens under this weird integral definition. First, the transform of a constant. I set up the Laplace transform integral from the definition I just gave you. Multiplied by the function is just multiplying by 1, so nothing happens there. I just need to do this integral. Well, this is actually a pretty reasonable antiderivative, and remember that the integration variable is t, so that s, the variable of the new function, will be left over after the integral. This is an improper integral, so I do need a limit, but in the end, I find out that a constant in the t domain turns into a reciprocal 1 over s. And that's already pretty strange. Now what about the function f of t equals t? Again, I set up the Laplace transform integral and integrate in the variable t. This is an integration by parts, and of course there is a limit to deal with the infinite bound of the integral. Here are the steps, and the result of all of this is it turns into 1 over s squared. Well, I can keep going. What about other powers of t? I've not shown the work here, but they're essentially all repeated integration by parts. The result of each is the multiplication by another number in the numerator and another power in the denominator. In the end, the transform of t to the n is n factorial over s to the n plus 1. Alright, so we have our first logic. Powers of t turn into reciprocal powers of s. That's not bad. Now what about some other functions? Well, let me look at the exponential. Here is the integral definition with e to the at as the function I'm starting with. And this is actually not a bad integral at all. In the limit, the result is the function 1 over s minus a. And this is where it starts to get very odd. Powers of t turned into reciprocal powers of s. But exponentials also turn into reciprocals, just with the subtraction of a constant. I mean, this isn't even the same kind of function at all. But yeah, this is how transforms work. Let me quickly give some more examples. I'm not going to show all the integral calculations here, just the results. But these are some pretty interesting results. So here's the transform of a particular piecewise function. The result is not a piecewise function, but something with an exponential in the numerator, but it's continuous. So even continuity doesn't necessarily get preserved under the Laplace transform. Here's the transform of a general power, not just an integer power, which is going to include transforms of square roots and similar functions, since those can be expressed as exponents. For whole number exponents, the transform was a factorial over a power. Well, the same works here, but the factorial becomes the gamma function. And that makes sense, since the gamma function is the extension of the factorial to other non-whole numbers. This means that the square root and similar functions do become reciprocal powers under the Laplace transform. Here are the transforms of sine and cosine. Like the exponential, these are surprisingly changed into completely different kinds of functions again. They become rational functions. And this is again very odd. And finally, there are even interesting and useful transforms of some non-elementary functions. This is the transform of the Bessel function of the first kind with parameter 0, which I defined in the series unit. I only know that a function is a series from that unit. I don't really know much about the Bessel function, just the series that expresses it. However, that strange series and the function it defines actually turns into a square root function under the Laplace transform. So there you have some examples about how the transforms work and what certain functions become after the transform. In the next few videos, we're going to do setup to try and explain why it all matters and eventually get to using these to solve differential equations.